We remember from our previous work that the density of states in K space per unit real volume is just a constant. It's 1 over 2 pi all cubed. And this is independent of the form of the band structure. It's independent of the form, at least, of our cubic crystals here. Here, for simplicity, we're going to continue with the idea that the crystal is some sort of cubic structure. And the side of this cube is going to be L. So the spacing between adjacent K values in any one direction is just 2 pi over L. Now, what we want here is the density of states in energy per unit real volume, and we'll call that G of E. So this is some function of the energy of the electron in the given band of interest. And this depends upon the band structure. The relation between E, the energy, and K, the wave vector, is not necessarily anything particularly simple. So in order to calculate this density of states in energy, we're going to need to know the relation between the electron energy, E, and the wave vector, K. So what we're going to do now is work that out for the case of an isotropic parabolic band. We're going to get the density of states for this particularly simple but rather useful approximation, a band in which E is proportional to K squared, basically, and is the same in that sense in all directions, so isotropic. Now, by assumption, in our isotropic parabolic band, the energy for a given K is going to be the energy at the bottom of that band plus this amount from the parabolic behavior, h bar squared K squared over 2 times the effective mass. So we're interested in number of states between an energy E, which would correspond to a specific sphere in K space, which we could figure out from this relation, and an energy slightly greater, E plus dE, which would be an energy corresponding then to this other sphere, a slightly larger sphere with a slightly greater K value associated with it, that corresponds to this slightly larger energy, an additional amount dE. So the number of states that we're interested in is the density of states in energy times the little bit of energy here, and that should be equal to the number of dots inside this spherical shell. Now, the radius then explicitly of our inner sphere is, of course, from this expression here, just K equal to the square root of 2 times the effective mass over h bar squared times E minus V. That's simply derived from here. So that's our K. And the radius of the outer sphere is larger by some small amount, dk, and since this is a very small amount, we can figure it out using the derivative. If we know how much K changes with E, then to find out how much K has changed, we use that derivative and simply multiply by the small amount of energy change, dE. So that would give us our dk here that we could then use to allow us to calculate the number of dots between these two spheres inside this shell. Well, from our expression for K, we can work out this derivative. Straightforward differentiation gives us this answer. So the volume of the spherical shell, the space between these two spheres here in K space, is 4 pi K squared dk. That would be the surface area of this inner spherical shell times the thickness of the distance between these two spheres. And we can work out what that is because we know that dk by definition is dk by dE times dE. And since we know dk by dE here, we have therefore an expression for dk by dE times dE. The K squared here means that we end up not with the square root of E minus V on the bottom line, but we end up with the square root of E minus V on the top line because we've taken the K squared here into this expression. Now, the density of states in K space itself is g of k, as we said before, 1 over 2 pi all cubed per unit real volume. So the total number of K states in this particular spherical shell, we've figured out the volume of this shell here in K space, is that volume times 1 over 2 pi all cubed. Now we need to introduce empirically here the idea that the electron has two possible spin states. So the total number of states between the energy E and the energy E plus dE is twice what we've been talking about. So we can call this density of states in energy, G of E, is 2 times what we just wrote down, allowing for the spin. In other words, we can say explicitly that the density of states in energy, the number of states per unit energy, per unit crystal volume, is given by this expression here. And that gives us what we can think of as an e to the half density of states. It's a very basic concept in the physics of semiconductors. As the energy E rises above the energy of the bottom of the band, that is, of the bottom of the parabola, the density of states rises as the square root of the extra energy. So, as we've shown here. So, starting from the bottom of the band and going up to higher energies here, the density of states grows as the square root of this extra energy here.